Okay, for this section of the video, we're going to be on page 248. And we're going to be doing example 8.7. And this is a sex-linked trait. And remember, the females is an XX. The males are an XY. And these chromosomes are called the sex chromosomes because they determine the sex of an individual. And there are not as many genes on the Y of the male, so that kind of skews whether something is going to be dominant or recessive, because sometimes there's just not a gene present on that Y chromosome. And we're going to work through some of these and you'll see how this works. And because this is sex related, we're going to use a superscript to show whether it's dominant or recessive. And it says a heterozygous red-eyed female is crossed with the red-eyed male. So we have a heterozygous, so here's our female, and it's heterozygous, and so the red eyes, we have two different superscripts here because it's red-eyed and it's hetero, and we're going to cross that, that's our little x, with a red-eyed male. Now because the red-eyedness is not carried on the Y chromosome, he had to have gotten that dominant red eyes from the X chromosome that he inherited from his mother. And so this is what our cross is going to look like. And we can set up a Punnett square. And we usually put the father across the top and the mother down the side. And we put our superscripts. And it follows the same principle as other Punnett squares, except we're also going to know if it's male or female. This one's female. And both of those females are going to be red-eyed. So 100% of the females are red-eyed. And let's look at the males. So here he got the the dominant. And here he got the recessive. So 50% of the males will be red-eyed. So he only had to get one dominant allele on the X chromosome that he inherited from his mother in order to become red-eyed. And so if the mother wasn't carrying the recessive, 100% of the males would have been red-eyed also. So you can see how this Y chromosome not carrying a superscript can affect how it turns out for the males. Let's do another one of these. Let's look at experiment 8.3. Let me get another sheet of paper here. And this is a sex-linked genetic trait. And this is about a disease called hemophilia, which causes people to bleed very easily from minor injuries. And in order to keep the bloodline pure and royalty, sometimes people would marry their relatives. And this is actually why there's laws against this, because if there's a genetic weakness, it's more prominent if you marry a relative. And that's why it's good to marry someone that's not related to you or far away from you as possible, so that anything that is genetically transmitted isn't more prominent or more likely to happen. So let's see what we've got here. We have hemophilia, and it is a sex-linked, and so we're going to designate the allele that carries it. It's going to be carried by the female, and we'll give it an H. Okay, let me read back here. People with this disease are prone to excessive bleeding. This devastating disease is a sex-linked recessive trait. That's why we're going to use the lowercase. Queen Victoria of England was heterozygous in the trait. So if she's heterozygous, she's got a dominant and a recessive. Thus she carried the recessive allele for hemophilia, but she had a dominant allele on the other chromosome, so she did not have the disease. So this was Queen Victoria. And so the only way her kids could have gotten it is if she had the recessive. Since this trait is sex-linked, we determined that the allele X lowercase subscript lowercase h is recessive. So to get hemophilia, you have to have this sex-linked trait. Draw a Punnett square that tells what the children's genotype might be. So we have Queen Victoria, and she was heterozygous for it. And she married, okay, he did not have it. So that means that on his X chromosome, he has the dominant trait because it's caused by the recessive, and because it's a Y, he's not going to carry it either because it's not carried on the Y chromosome. So let's go ahead and look at our girls. So 100% of the girls will not have the hemophilia. But if you look at this, one of them is going to be a carrier. So we have one that's a genetic carrier because this girl has the recessive trait. She ends up looking just like Queen Victoria. She's carrying it. So let's look at our males. This male will not have it because it's caused by the recessive. But this male will. So 25% of the males will have the hemophilia because it's caused by the recessive. This guy's going to have it, and chances are if he probably wouldn't survive, but if he passed it on and this was dominant, we would end up with a bunch of carriers that wouldn't express it, and none of the males would. They're not asking you for this information though. This is what they're asking you for. Okay, the next one, their son Leopold was hemophilia. What was his genotype? We know his genotype was this. Hemophilia can also be present in females. Write a Punnett square to show how it is possible to produce a hemophiliac female. And so for a female to have hemophilia, we're going to have a double recessive, a homozygous recessive trait. And in order to get that, here's the dad, here's the mom. This one's going to have to be, the male's going to have it. And the female has to be a carrier. Let's make this one not have it. Let's make it dominant. And so in this case, we would have a female that would get the hemophilia and a male that would get the hemophilia. Now, if this female was recessive on both, then all of the offspring would get it. But that would also mean that the female had it and the male had it. If the female had it, she probably would die in childbirth, so it wouldn't have happened anyways. All right, well, let's go ahead and look at the blood typing. Let me get a new piece of paper. And there's 4 blood types. You can either be A, B, AB, or O. And interestingly enough, O is a universal donor. It means a person with O blood can give blood to AB, can give blood to B, can give blood to A. But A can only get A, B can only get B, and the same with organ donation. An O is a universal donor. They can give organs to any other blood type, and you'll see why in just a minute. Usually an A also carries an O, but not necessarily. So when you're A, you can either be AA or AO, and B can either be BB or BO. And this one, it means one of your parents was A and one of your parents was B, and this is what they call a codominance. There is no dominant and recessive. It just becomes codominant and creates a new group. And so let's look at this. I happen to know that I'm A, and I happen to know that my husband is O. So I don't know what this one is. Actually, I know that's O. And so our kids had a chance of becoming A or O, 50% A and 50% O. And I happen to know one of my sons is A and one of them is O. And I know that I had to have carried this O for me to get a child with the blood type O. And so it's interesting, and I happen to know that my dad, from his dog tags in the military, he was blood type A, and my mother is blood type O, and so that's how I ended up with AO. So if you know your blood type, you can figure out your parents' blood type if one of them knows it, and hopefully you will find out that you are indeed your parents' child. So let's take a man who has blood type B, and he marries a woman who has AB. What will be the blood types of her children? So the man is B, and we know it's BO because if it would be codominant, he would be AB, and the woman is AB. And so we can see that they have a 25% chance of having an AB blood type in one of their children, 50% chance that their child will have a B blood type, and 25% chance of their child will have an A blood type. But let's say one of their children turned up to be O. Is that possible? Or is somebody lying about their children? Say the child went and got tested and found out he was O, and then he knew that he was adopted. And they do this all the time, and you always see it on Law and Order and stuff like that too. They can determine a lot of things just by this 4 section of blood typing. I'm going to give you a couple of blood typing questions to do. Those are kind of easy ones to do on Juno. And I want you to keep all of your work and give it to Mrs. Shu so that I can check it, but I also want your answers entered in Juno. That's the end of the video.